Assalamualaikum, very good morning. This week we continue to our second guided lab, which is pre-lab 2. We are titled Series and Parallel Circuiting of Resistors. Okay, so basically this topic is related to Ohm's law. The objective here, upon completion of the experiment, students should be able to, number one, determine the total resistance of series circuiting and parallel circuiting of resistors. Number two, validate the measured currents and voltages at respective points in a circuit using Kirchhoff voltage law, KVL, and Kirchhoff current law, KCL. The general information, 3.2.1, series circuiting of resistors. If resistors or quiet general loads are circuited in series, the same current flows through them. The size of the current is determined by the applied voltage U and total resistance R total. Figure 3.1 shows series circuiting of resistors where the total resistance of the circuit is equal to the sum of all resistance of each series circuiting resistor. Okay, so basically, just for recap, in your series circuiting, in every line here, at every particular point in this series circuiting line, the total current will be the same, okay? While the partial voltage for each resistance will be different, okay? You can see here, I equal to U over R total, where R total is equal to R1 plus R2 plus Rn, okay? A partial voltage is applied to each individual resistor. The sum of all the partial voltages given the total resistance U equal to UR1 plus UR2 plus URN. Experiment, okay? By measuring current and voltage, prove that the current is the same at every point in a series circuit and that the sum of all partial voltage give the total voltage. Experiment procedure 3.31. Set up the experiment according to circuit in figure 3.2 and apply 10 volt DC to the input. Number 2, break the connection between AB, okay, here is AB, CD, here, EF, and GH, one after another. Okay, I repeat here, one after another, and measure the current through the series circuit between the test point. Then measure the partial voltages at test point BC, DE, FG, as well as the total voltage at test point BG. Enter all measured value in table 3.1. Okay. Number 4, compare measured result with calculated result. Okay. So basically, like the previous lab session, we will get a slightly or maybe a bit different in the measured value compared to theoretical data. So we need to know what is the actual value of the resistance, because the main thing that affect the measurement is one of them is resistor. Okay, even it's written 100, but the actual value is not actually 100 ohm. So this is 3.2. So basically, I just go through first the instruction. So this is level 3.2. Measure current and voltage drop at respective test point. So you can see here, first we need to measure the current and then partial voltage and then the total voltage. here, mentioned here is measured and calculated. Basically, the calculated, you can add more here. The calculated based on the actual value of the resistance. Okay, because we don't know what is the actual value of the resistance. So we do the resistance test, then we know. Okay, so this is the question. You can answer this in the discussion later. Then parallel circuiting of resistor. The general information. If resistors are quite generally loads are circuited in parallel, they are all under the same voltage. A partial current is flowing in every branch of parallel circuit. Okay. The sum of all partial current gives the total current. Figure 3.3 shows parallel circuited resistor where the total voltage and total current are given by U equal to UR1 equal to UR2 equal to URM. And I total is equal to I1 plus I2 plus IN. Okay, so basically, theoretically, the I that flowing over here is different with this one and this one. Okay, but the voltage is the same for the parallel splitting. The size of the partial current is dependent on the applied voltage and the realistic partial resistance. Okay, so this is a formula. The total current value is dependent on the applied voltage and the total resistance. I total equal to U over R total. The following formula is used for calculating the total resistance. So this is the formula for R total. For only two parallel circuited resistors. So this is the formula. Another possibility for calculating the total resistance of a parallel circuit of resistor is the addition of the electric conductance of the individual resistor. Okay, so this is the conductance formula. Okay, now we go to the experiment. By measuring current and voltage, prove that the voltage on all resistors in a parallel circuit is the same and that the sum of parallel current is equal to the total current. Okay. The experiment procedure. Set up the experiment according to figure 3.4 and apply to 10 volt DC to the input. Break the connection between A, B, C, D, E, F, G, H, and K, one after another, and measure the current each time. Okay, one after another means we need to do it one by one. Okay, we go to A, B first, break the connection, put ammeter. Once we get the measurement, we reconnect it again, and then we break CD, put ammeter, and continuously repeat again until LK, right? Enter the measured values in table 3.2. Number 5, compare measured result with calculated result. Okay. So this is figure 3.4. So this is table 3.3. Okay, you can see here measured and calculated. The calculated, you can add another one for the actual value. Right? But for this experiment, you can calculate first based on 100, 220 and 470 for your reference question. So this is the question. So that's all for the instruction for guided lab 2. We will continue to the lab session. As usual, I will do the lab session, get the reading, and you guys will do the lab report. Okay, thank you.
Okay, now we continue to the experiment, the actual experiment. So basically, after you read the general information, if you can see in a figure 3.1, so basically you have to create the experiment based on figure 3.1. Okay, sometimes the student when they see figure 3.2, they confused why they see the the multimeter on the AB, and then why there's voltmeter between D and D and E. Okay, so actually it's a schematic diagram of figure 3.1. Okay, if you understand the diagram, you should know when to disconnect and create the connection AB, CD, EF and HG. Okay. Okay, now we continue to the experiment 3.3.1. Okay. So basically we have to take the measurement and input every data in table 3.2, measured current and voltage drop at respective test point. Okay. So basically you can calculate the theoretical data for A, B, C, D and EF and even HG. So if you understand the theoretical knowledge of series circuiting, you should know what is the value for those current at particular point. Okay, so now continue to our actual circuit. So basically the circuit will be like this. Okay, so from here the power supply. Okay, so basically here R1, R2, R3 and then go back to the power supply. Okay, so I think I miss here HG. Okay, put it here. So this is our circuit. So first of all, we have to measure the actual value of the resistance. So basically, actually you can do like the previous experiment. First, you calculate the theoretical value for 100, 220 and 470 for every particular point in series circuiting. And then when we come to the real experiment, we also can calculate the theoretical value of the value of the particular point based on the actual resistance using the multimeter. Okay, so now we go to this one. So this one is 100 ohm. This one is 100 ohm. This one is 100 ohm. So multimeter we'll be using. So I'm using digital multimeter. I'm using the resistance. Okay, put here. You can see that it's 100 ohm. Okay, So this is good, 100 ohm. So you can jot down it's 100 ohm. And then this one is 220 supposedly. So it is 200 and 216.8. Okay. Now we have the third one. So this one will be 460. Okay, this one is 460. $461. How about selling slash? Okay. So it's 460 ohm. Okay, 0.460 kilo ohm. So it's 460. Okay, in the papers is 470. It's okay, you can calculate first 100, 220 and 470. Okay, now we want to create the first one is series circuiting of the resistor. So you can see here we have breadboard, so make sure everything is off first. So this power supply already in off mode, so basically I already connect this one to, this one is from power supply, and then from the power supply I connect to here. Actually I can put here, right, and then I put it here. Okay, so this is our 100 ohm. And then from 100 ohm I connect it to here. To here. Okay, I put it this way so that it's easier for you to see how this series circuiting is look like. Okay, I try to do it as close as to schematic diagram in the manual. So the third one is 460 ohm. Okay, maybe I can put it here. Is it too far or not? Okay, and then from here to here I do 2 jumper because I want you to see it clearly, the HG. Okay, so this one connect to the power supply, right? Okay, now so this is our series circuiting of the resistor. Okay, the breadboard ABCDE is internally connected. That's why I connect here. No connection between this and this, so I connect here because it's already connected internally, and connect here to here. 216.8 ohm, and then connecting to 460. Then from here go to this jumper, and this one go to this jumper and go back to the power supply. Okay, now we go to our first measurement for test point AB. Okay, test point AB. So how to create AB? Okay, how to create AB? Okay, so AB is to measure the current. So for measuring current, you need to do a series connection for the ammeter. Okay. Okay, now we want to measure AB. So I break connection here, A and B. Okay, since we have to create a series connection for emitter, right? So I already turned off the power supply. Okay, make sure all of the connection is good. We select the right connection, the right mode here. So we're using milli ampere. It will automatically select the range for you. Now I will on to see what is the value in AB. So stated here is AB is equal to 12.6 milliampere. So you compare with your calculated measurement 400 ohm and actual value for 100 ohm resistor is 100 ohm. Right now is 100 ohm, so it should be the same lah. Okay, more or less the same. 12.6 milliampere. Okay, now turn off. So we create the connection CD. So I connect it again. CD is the breakpoint of between R1 and R2. So I will break the connection. Okay, put somewhere over here. So there's no connection between this and this. Okay, because there's not between numbers there's no connection. Okay, I put here and here. Okay, you can see here. Same 10 volt, but the actual resistance is 216.8. Okay, maybe a little bit different with the calculated data. So now, what is the value? So it's still the same. CD is 12.6 milliampere. Right. So if you understand the series skirting concept, the current for each point should be the same. Okay. Then we go to CD and then EF. So between this and this one. So I break connection here. So there's no connection since I put it line here and line here. So there's no connection here, no. So put it here and here. Okay, you can see. So this is EF. I put the data 10 volt. So you can see here 12.6 millivolt. So EF equal to 2.6 millivolt, not volt, it's ampere. Okay, current. Sorry. Turn off. Okay, make sure turn off every time you want to change the connection. Okay, put it back here. Now we want to see HG. So I break the line over here. Do the connection here and here. Okay, supply. Apa ni? So the measurement is HG is 12.7 milliampere. Okay, how about here? So it's 12.6. Okay, 12.6, not 2.7. Okay, for 10 volt. So we finish HG. So next we want to measure what else? A, B, C, D, E, F, G, H, and then the total voltage is BG, yeah, BG. No, the next one will be the partial voltage. Okay, partial voltage will be BC. Okay, partial voltage, you need to measure BC, DE. Need to do a parallel connection. So this one is FG, right? Because this is G, this is H, FG. Okay. So if you understand the concept, we will measure voltage, partial voltage for R1, R2, and R3. Okay. On dulu. Okay, now we want to measure partial voltage for BC, DE, and FG. Okay. First, make sure everything off first. Okay, change the mode to voltmeter. Ready, guys? So this is BC. Okay, put here and here. Right. Okay, BC on. The connection. Okay. Make sure everything is connected. Okay. Okay. Again. In here. So this is BC. So you can see here B and C. It is 1 point. Wow. 1.232. 1.2. Again, wait. Okay. 1.265. 1.265. 1.265 volt, and then for 216.8 is 2.747. Then for 460 is 5.82. 5.82 volt. Okay, this one is FG. Okay, and then we need to measure BG. Okay, the total voltage. So from B to G, BG. Okay, so basically it's from here and here. It's 9.84 volt. 9.84 volt. Okay, that's all for series circuiting. Okay, now we want to do the connection for parallel circuiting of resistor based on schematic diagram figure 3.3. Okay, and then we go to 3.4. Okay, we already state here where to do the connection. So basically R1 100. Okay, maybe I can put it here, in here. Okay, and then 216.8 I put it here. And here. Maybe I can put it a little bit far so easy for you to see. So this one I put it here and here. Okay, since we are using breadboard, so there's no connection between this and this point, so I put here one here, right, then I put it one over here and put here. Okay, this one I put here. So this is from power supply. Okay, so this represent the parallel 1, 2, 3. Okay, now we need to do the lower part connection from here and connect it to here. Okay, and then need another one. This one I adjust it here. This one I put it here and here. Okay, why this one is under one line? Because in the alphabet in breadboard there's internal connection. Okay, from here connect here. So and then from negative terminal power supply put it here. Okay, so this is our parallel circuit. Okay. Okay, now we want to do the measurement for AB. Okay, so make sure everything off first. I pull out here to break the connection, and then put it here. So this is AB. Okay, this is AB. Okay, between this and this point. Okay, so now we want to see the current. So the current is 340.4. milliampere. Okay, now we want to do the reading for CD. Okay, so I break the connection here. That's it. Okay, so you can see here the reading is 93.3. So that one is for CD. Now we go, we connect again this one. Okay. Oh, panas. Okay. Everything is okay, and then this one I break the connection. Okay, and then salah. Okay, now we want to measure CD. Okay, So I break the point over here between this and this. So this is CD. Okay. So this represents CD. Turn on and you get 94, not 94. 95.6. And then we go to EF. EF. Oh, panas. So I reconnect this connection again. So EF here, I break the connection. So connection here, EF. Put emitter. Okay, you can see the point here between. So we supply voltage. So you can see the reading over there is 43.1, 43.2, 43.2. Sembilan. And then we connect, we do the third reading for GH. Okay. So the reading is 20.1 milliampere. Okay. Okay. So basically the total current, the overall current should be, if you understand the concept of current in parallel circuit, I total is equal to I1 plus I2 plus I3. So you can see in experiment data here, it exceed 140.4 that we measure in AB. Okay, I think we can do the measurement again. Okay, it's not a problem to recheck whatever measurement that you have already took. Okay, so let's say I put it like this. Okay, from the power supply, and then this one I check it here. Let's see how it goes. If you can see here, R1, R2, IR1, IR2, IR3. If you plus all of it, it should be 9. So 5 plus 3 is 8. 9 plus 4 is 13. Plus 2 is 150. So it should be 158.9. Roughly 158, 160. Okay, so let's see what is the actual total current. Okay. I think I misplaced this one, so we can put it here. Betul on. So if you can see here, the total current is 158.3. Okay, plus minus, is near to the total current that we measured just now. Okay, so 108.3. So it should be 158 milliampere for the total current in this circuit. Right? Now we want to measure partial current, voltage. Okay, test point DK, FK, and HK. Okay, I think I should do the test point DK, FK, HK first, right, for voltage. But if you understand the partial voltage in parallel circuit, it should be the same amount. So first we need to do for DK first. And now we want to continue for measuring a parallel circuit for the voltage. So now we want to measure DK. Make sure you change the mode here to voltage, to volt. Okay, this one we redo the connection. Okay, since we want to measure voltage, we just slot in parallelly. So this one is DK, right? Okay, so this one is DK, this one is DK. Okay, so I will turn on. So the volt over here is 9.9 volt. DK is 9 volt. And then this one is FK, right? FK. So this is FK. Turn on. So it's roughly near to 9, so 9.0. I think it's 9. Just put it 9. So it's 9 volt. FK is 9 volt. And then HK is turn off. HK is here and here. So this is HK. .04. So roughly is 9. So total voltage, right? Total current. No, they want to see the AB. Where is AB? So AB and LK. AB and K. AB. So AB we already took the measurement is 158. So this is AB. Okay. You can see I took all the measurement here. AB. And then LK. So LK will be under here. So turn off, change the range to ammeter. Break the connection. So this one negative terminal. So this is positive terminal. Okay, turn on. Oh, now you can see the current goes up. So the one that we took at AB is 158. So what we can see in LK, is it increasing? can see here, maybe there's problem in this jumper. Okay, if I took it here, it goes up to 160. 163.6. Okay, so LK is 163.6. Okay, do you want to me redo for AB again? Okay, maybe I can go for AB. So let's say I put it here. Okay, then AB I put like this. So this is A, this is B. Okay, I just decrease the number of the jumper. Need to see how it goes. Oh, huh. So if you can see here, the number go to 144.6. So maybe we can use 164.6, sorry, not 46, 164.6 milliampere as the result. Okay. Okay, that's all. I think that's all for this lab. Okay, hopefully you can do the discussion on this guided lab too. Thank you.